I take this opportunity to welcome our resource person, Professor Srinivas from the Institute of Mathematical Sciences, Chennai. He has been there since 1996. He is an expert in analytic number theory, algebraic number theory, modular forms and elliptic curves, mathematical aspects of cryptography, etc. And he has published many research papers of high quality, all in reputed journals, and co-edited 2 volumes of JRMS, that is Journal of Ramanujan Mathematical Society, and co-edited one recent volume for RD Ramanujan Journal, and he did his PhD from EIFR Mumbai on some analytic properties of the Riemann zeta function, and his MSc and MPhil was from University of Sambalpur, Odisha. He is a member of Executive Council of Ramanujan Mathematical Society from 2010 to 2019 on various positions, a member of Board of Studies of various institutions like NIT Roorkela, Central University of Tamil Nadu, and co-managing editor of RD Ramanujan Journal. He has been part of this MPPS program since 1998, co-organized interactive mathematics training camps since 1998, a regular speaker in Inspire programs, and has organized several AIS programs, teachers enriched workshops, and lectured in many AFS programs. He also loves giving popular talks in mathematics, has given 2 programs on Ramanujan's work in both Hindi and English, which were broadcasted by Air Delhi. It's an honor and privilege for us. I'm sure we will be enriched by this webinar. Once again, I welcome you, sir, on behalf of the Department of Mathematics, University of Calicut. Please, sir.
I thank the organizers for doing such a wonderful enrichment program. I'm sure it has helped many participants, research scholars, teachers, and I really thank Professor Kalyan Chakravarti, who is the director of JSOM, who has been in touch with me, and he was telling me that there are interested people here and we should help them. I said, okay, fine, we will do that, and that's how it started. So this topic is very interesting. I don't know how you selected India, mathematics and Ramanujan, but it sounds very amusing and also interesting. Okay, what was the rationale behind it? India, mathematics and Ramanujan?
Actually, sir, I put a broad area. Then we applied for the sanction of this program. Okay, and then I thought later I can change it by consulting with the resource persons. What they are.
But
so everyone agreed that.
Non-trivial, sounding. Very good. Yes. So the title is on Ramanujan's lattice point problem. So what is a lattice point problem? There's a whole lot of literature which goes in the name of lattice point problem. So let us try to understand what is lattice point problem. So the first question is, what is lattice point problem? It is very simple to state. All right. So we are interested in finding in the set of points xy, okay, in the xy plane, such that both x and y are integers. Okay, with x and y belongs to z. So such points, when you collect, they form a lattice. All right, and the lattice point, so they form a lattice. And the lattice point problem is the estimation of such points. Okay, estimation of such points inside a large domain. Large closed domain, okay? We are bounded by some simple closed curve is called lattice point problem. So take a simple closed curve, count the number of points which have integer coordinates. And the thing is, as the length of the curve goes to infinity, as the curve expands, how many lattice points are there? Okay, that is the, otherwise if it's a fixed one, it is very easy to count. All right. So classically, there are two very famous lattice point problems. One is by Gauss, the famous mathematician Gauss, okay, and that is called circle problem. Okay, what it does, it asks for the number of lattice points inside a circle. So when I say inside a circle, as the radius of the circle goes to infinity, count the number of lattice points. Okay. And the other famous one is Dirichlet, by Dirichlet. And this is called Dirichlet divisor problem. And here, one is interested in the number of lattice points inside a hyperbola. Inside a hyperbola. I will discuss these things a little later. Now the third one, which is the main topic of today's talk, is by Ramanujan. And what is Ramanujan's lattice point problem? It counts the number of lattice points inside a right angle triangle. All right. Again, this is related to the first letter, the first famous letter by Ramanujan to G.H. Hardy. And we will see some of the developments that has taken place. So let us first discuss about the circle problem of Gauss. Okay. So what is Gauss's circle problem? Consider the circle. Consider the circle. Let's say u square plus v square is equal to x. X is bigger than or equal to. And let the a be the number of points with integer coordinates. That is the lattice points, set of all mn. And n belongs to z, such that m square plus n square is less than or equal to x. Okay. This is what we want. We want to find an estimate for a, the number of points inside. All right. The easiest thing which Gauss did was the following. So let us draw a circle first. So let me draw a circle. Okay. So there are lattice points inside this. So let's say sorry for the bad drawing. Okay. Think of these as straight lines. and each of these points are lattice points. All right. So we have split it into small unit squares. All right. And we want to count how many of them are there as x goes to infinity. All right. So what Gauss did was, to each lattice point, he associated a square. All right. So to this lattice points, let's associate this square. To this lattice points, associate this square. Okay. To this lattice points, associate this square. Okay. So the leftmost bottom point is associated with this unit square. Now to count how many lattice points are there, one can count how many unit squares are there. Right. So, but you know, these squares are a little protruding outside. You see? To this point, we associate this square, it is coming out. All right, this square. Observe that the maximum, if you draw a circle, see the diagonal of this unit square is square root of 2. So, if you draw a circle of radius, let's say root x plus root 2, the bigger one, then all the squares will be inside this bigger circle of radius this much. All right. And similarly, okay, if you draw a circle of radius square root of x minus square root of 2, all right, which is inside this one. Okay, then the area of this square, this circle, is slightly less than the total number of lattice points, because some lattice points are outside this. Okay, like this. So this observation tells us that to each lattice point, so what we did, to each lattice point Pi, let's say, which has coordinates ui, vi, let's say, okay, associate a unit square. Let's say Qi. What is Qi? Qi is set of all uv such that u minus ui is less than half, v minus vi is less than half. All right. This is what we did. So each unit square is like this. All right. And then we observe that there is a 1-to-1 correspondence between the lattice points Pi's and Qi's. All right. In fact, the union of all the area, union of all this unit squares, union of all this area Qi's, okay. I would rather say, union of, if you take the area of all these Qi's and take their union, this will be less than pi times the area of the larger circle, which is pi times square root of x plus square root of 2 square, and the union of the area of all these squares will contain the area of the smaller circle. Okay, that is pi times root x minus square root of 2 square. All right. or the number of lattice points, which is this, A is the number of lattice points we have denoted, is less than pi times square root of x plus square root of 2 square, which is bigger than pi times square root of x minus square root of 2 square. And this tells us that A is A minus, if you open up this brackets, both sides, so the first term is x times pi, so A pi times x, and then you get pi times square root of x and all this. So A minus pi x is less than some constant times pi square root of x. This one can write it as A is equal to pi of x plus, if we are not bothered about these constants, then one can put a O symbol and square root of x. So this tells us that the total number of the lattice points inside the circle of radius square root of x here is pi x, which is the area of the circle, and square root of x is the perimeter. 2 pi square root of x is the perimeter. Therefore, this gives that the number of lattice points inside a circle of inside a circle is about the area of the circle and with an error. This is the error, with an error of the order of its perimeter. All right. In fact, more general. So lattice points inside the circle, we have seen it as area of the, it approximated by the area of the circle, and when you approximate, you get an error. The error is of the order of the perimeter. All right, and this is true in general. In fact, this is true in general. In fact, Steinhaus he showed that if you take any arbitrary for any closed continuous curve J, take any closed continuous curve J with area, let's say F, and let's say the length of the curve, length L, which is bigger than or equal to 1. If you take any curve J with area F and length of the curve L, then the number of lattice points on or inside the curve is the lattice points A. It is of the area F with the error of the order L. So it is true in general. All right, and therefore, so what is Gauss problem in number theory? So the Gauss circle problem asks the following. What is the actual problem? You take R of X now as number of points Nm, with Nm belongs to Z, n square plus m square less than or equal to x. These are lattice points. I put Rx as area of the curve pi of pi x. It looks like number of primes. Pi x plus O of x to the power, let's say put theta. Okay. So the Gauss problem is find optimal value of theta. This is the problem. All right. And it has very interesting, history. So actually those who are, there were many questions in previous sessions which I attended. Somebody was asking, what is the way to do research, how to solve big problems, and these kind of things. So one should also look at the history of the problems. Okay, one should study the papers, the literature, okay, to get an idea of how people do research. What kind of, what do you mean by, adding something to mathematics? All right. So I would like to give a one slide glimpse of this problem. So Gauss, we have seen, he has obtained it in the beginning of 19th century. Theta is equal to half, right? This we have seen. Square root of x is what he has got here. Later, Sierpinski. So Sierpinski, this is around 1906. He looked at this problem and he showed that theta can be taken as something around 1/3. Okay. Then this famous mathematician van der Kerkhove, who was responsible for inventing many ingenious techniques in analytic number theory, namely the exponential sum techniques. Okay, there is a famous method called van der Kerkhove's method. It estimates exponential sums in a non-trivial way. He showed that, in fact, theta can be taken as 1/3 minus epsilon for some epsilon positive. From here to here, 1/3 to less than 1/3, it required a lot of new ideas. And once van der Kerkhove invented that method, later Landau, Littlewood, the Hardy Littlewood, Wallfish. So around 1924, they improved it further to theta less than 3303. See, this is around 0.33333. So there is an improvement in the third decimal place by Landau, Littlewood, Wallfish. Later again, Wallfish, around 1927, he proved that theta can be taken as something less than 3299. So there is an improvement in the second decimal place. And Nyland, around 1928, he showed that theta can be taken as 0.333. 3292. So, okay, the fourth improvement in the fourth decimal. Titchmarsh, in 1934, he showed that theta can be taken as 3260. So again, see, there is an improvement in the third decimal place. L.K. Hua, in 1942, he proved that theta less than 325 is admissible. So there is an improvement in the third decimal place. Chinese mathematician Chang Jin-rang is a very famous mathematician. 1963, he showed that theta can be taken as 0.3243. So there is an improvement in the third decimal place. Novak, just to give an idea of, the development of mathematics. It's in 84. Okay, theta less than or equal to 324074. Okay, so there is an improvement in the fourth decimal place. Again, Kolesnik. These are all well-known names in number theory. 1985, he showed theta can be taken as 32400. Very recently, Ivaniak and Mojochi this is around 1987. They showed that theta can be taken as less than 7 by 22, which is about 31818 and 1818. Huxley, Martin Huxley, in 1993, and again later in 2003, he showed that theta can be taken as 3150, and in 2003 he showed it as 3149. Okay, this is the latest one. All right, so you see, from in 100 years, how much improvement has come? 0.33332. I mean, after Gauss is 0.5. Later, Sierpinski, he proved it 0.33333, and the latest one is 0.3149. All right. So, by working on these problems, people have developed many new techniques. Okay, and those techniques have been applied in other parts of mathematics to get new results. All right. Now, how far can we go? The question is, how far can we go? How far below? Okay. So, in this regard, Landau and in 1915 and G.H. Hardy, they showed that you cannot go below 1 by 4. Okay, they showed that theta, that exponent theta, has to be bigger than 1 by 4, so which is 0.25. All right, so we cannot go below, but we are far away. We are at 0.3149. All right, so therefore this problem is still interesting, and one requires new techniques. All right. I may also say that there is a result by K.S. Gangadharan. In 1961, who showed that, the error term, so that Rx, if you write it as the main term, is pi times x, plus this is omega of x to the power 1 by 4 log x to the power 1 by 4, and then log x to the power 1 by 4. So this omega symbol means that, so there are infinitely many x's for which this quantity is bigger than, the error is bigger than x to the power 1 by 4 log x to the power 1 by 4 log x to the power 1 by 4. This is just opposite of O term. And K. Soundararajan, the famous Indian young mathematician, in 2003, he showed that, in fact, this can be taken as Rx as pi times x plus omega of x to the power 1 by 4 log x to the power 1 by 4, and then you have log x to the power 3 into 2 to the power 1 by 3 minus 1 by 4 by log x to the power 5 by 8. So you see, this logs, multiple logs are very familiar to number theorists, but it may look very amusing to non-number theorists. But these are very common features, and they come up when you compute very carefully. All right. So this is all about circle problem. The second problem is Dirichlet divisor problem. All right. So here one is interested, so maybe I will not write too much. Look at the hyperbola, let's say. Let me draw. Okay. So let us say so let S of x be the region defined by u is bigger than 0, v is bigger than 0, and uv less than or equal to x. So this okay. Then divisor problem is compute dx. Okay. Number of lattice points between the axis of axis and the hyperbola uv is equal to x. Okay. But don't count not on the axis, okay? Because the axis, this x-axis, u-axis and v-axis, they will contain infinitely many So you don't count on, but between the axis and the hyperbola. Okay. So you can count the points on the hyperbola, if anything on the hyperbola, but not on the axis. All right. Therefore, mathematically, dx can be written as number of lattice points mn, such that mn belongs to z, mn bigger than 0, mn less than or equal to x. Right. In other words, you can write it as summation n less than or equal to x d of n, because this is same, because mn less than or equal to 1, mn less than or equal to n, because this is same thing as count all mn less than or equal to x, right? And that is same thing as writing this in terms of the divisor function. Where what is dn? dn is the device, number of divisors. So d divides n. All right. I hope it is clear. All right. So how to count this? How did Dirichlet count this one? Okay. Now observe that this hyperbola. So if I remove this one and I say this is if I look at this hyperbola is symmetric to this line. All right. So therefore, observe that the area under the hyperbola if I write the hyperbola as QD is equal to X, all right. This is symmetric with respect to the line Q is equal to D. So I take the line Q is equal to D, then this area is symmetric to this area, right? That is clear. Therefore, if I take this line, what is this line? So if I take this line, so this is my, sorry. So if I take this Q is equal to square root of X, all right. So Q is equal to square root of X and count the area which is under this one. So this, okay, this area is same as this area. I hope I'm making sense. So this area, we have this one here. So the area, this is same as the area up to this. Now why we are doing is, it is easy to count the area, this area, it is pretty easy to count, all right. So since we want to count total area of this, because we know that the number of lattice points is approximately equal to the area under the curve. So we want to count the area of this. We want to estimate the area. What is the area? Therefore, so what we do is let N1 be the number of lattice points to the left of the line Q is equal to square root of X. So this is this to the left of this line. Okay. So all the lattice points that are here. Let's say they are N1 of them. Okay. Therefore, what will be the total number of lattice points? That is dx. Since this area is same as this area, so the total area is this area to the left of this line, 2 times that, minus the area of this square, whose length is square root of x, side length. Therefore, d of x is 2 times area N1 minus square, area of the square, that is square root of x, the side. So this is what is Dirichlet's way of writing. And therefore, now how to count the number, the N1 area? So area, counting area is pretty easy. So this is 2 times. For any fixed, see this is Q, this is D. For any fixed D, count the total number of Qs and then vary over Q. That means for any fixed D, sorry. So this is X by Q, and Q is less than or equal to square root of X minus square root of X square. So N1 is nothing but this one. Okay? Because we are looking at, I hope this is clear. You take any line here, the number of points on that line will be X by Q, and vary Q from here to here. All right. Therefore, and then simplifying this, this is nothing but X by Q. Open up X by Q, the integral part of that will be X by Q with some small number. So Q is less than or equal to square root of X. What happened to 2? 2 is here, minus, open up square root of this integral part. So this can be written as square root of X plus O of 1, entire square. When you simplify these things, so this is 2 times, our X comes out, and then this is 1 by Q plus Q less than or equal to square root of X plus O of square root of X. This will give you minus X plus O of square root of X. All right. So which is nothing but 2 times. Now 1 by q up to square root of x. If you sum it, that will be along log of square root of x. So log of square root of x is 1 by 2 times log x. So let me write it, square root of x. This is this log of this plus gamma plus 2 of 1 by x. It's easy to show. So use this formula, summation 1 by n less than or equal to x, E is equal to log x, is about log x plus gamma plus O of 1 by x. So therefore this will give you x log x plus 2 gamma minus 1 x plus O of square root of x. This is what Dirichlet obtained. Okay. So if we write Dirichlet divisor problem, as d of x, counting the number of points inside the hyperbola but not on the axis, bounded by the x by the two axes and the hyperbola, then d of x is x log x plus 2 gamma minus 1 x, because this is the area which is bounded by the curve and the axis, plus if we write it as x to the power alpha, then Dirichlet, he showed that alpha is equal to half, as we have seen here. And later again, Wander Corput, I will not write all the results. He showed that alpha can be less than. All right. So from 1/2, 1 by 2, he brought it to 1/3. That is a big step. And once he brought it to 1/3, then the refined estimation of the exponential sum finally led Huxley recently, Martin Huxley, in 2003 to show that alpha is 0.3149. Again, how small can we make it? We can't make it less than 1 by 4, because again Landau and Hardy, they showed that alpha is at least 1 by 4. For infinitely many x, it takes the value 1 by 4, at least 1 by 4. All right. So we cannot make it less than. Now, if you look at the developments, I mean all the progress, both the things are similar. The results of both circle problem and divisor problem, the end results are same. I mean the estimations that you get, if you see all this that I mentioned here, for theta, they are same for alpha also. So exactly the same results for Dirichlet, divisor problem and circle problem. The reason is that when you look for optimal error term in both circle and divisor problem, then the problem for circle problem essentially both circle and divisor problem reduces to estimation of sums of the type R2n e to the power 2 pi I square root of nx, where n less than or equal to n. This is for the circle problem, sorry. And for the divisor problem, dn e to the power 2 pi I square root of nx, n less than. So both the problems reduces to estimation sums of this form. R2n is the number of ways of writing n as sum of two squares. And dn is the number of divisors of n. So you see the forms are similar, both. Okay? And therefore the results that you get are same. So one would be wondering, like, how come, there are two different problems but same results, end results are same. So this is the reason. All right. Okay, now we would discuss about lattice point problem, Ramanujan's lattice point problem. This is not so well known, I suppose. So let us, the famous letter of Ramanujan, as all of you know, contains many interesting and important path-breaking results that Hardy could immediately notice that this must be coming from a first-rate mathematician, and therefore he invited Ramanujan. And then what happened is a history. Okay? So in one of the problems that is mentioned in that letter, so S. Ramanujan he writes, okay, what does he write? The number of numbers of the form 2 to the power u, 3 to the power v less than or equal to n is log 2n, log 3n by 2 times log 2, log 3. This is what he writes. All right. When it reaches Hardy, Hardy could immediately know that this is very interesting, and then he pursues it further, Hardy. So what Hardy does, so if you look at 2 to the power u, 3 to the power v less than or equal to n, take the logarithm, then this becomes u log 2 plus 3 v log 3 less than or equal to log n. Right. So Hardy tries to generalize it. Okay. So he puts omega as log 2, omega prime as log 3, and eta as log n, and then says that Ramanujan asserts that the number of solutions of the inequality what is the inequality? U omega plus V omega bar. See, this is omega bar. So U omega plus V omega bar less than or equal to eta, of course bigger than 0, subjected to the conditions U bigger than 0, V bigger than 0 is approximately eta square by 2 omega omega prime plus eta by 2 omega plus eta by 2 omega prime plus half. I mean, if you put here log 2n is log 2 times log n, log 2 plus log n, log 3n. So split all these things and then do this, you will get this expression. All right. So this is how Hardy treats Ramanujan's problem. All right. Of course, as some of the problems with one can find in Ramanujan, there are some mistakes. This half has no place to exist. Okay. But there is a half in Ramanujan's assertion, which one knows that half cannot be there. Okay. So therefore, what is Ramanujan's lattice point problem? So we can put it as, let omega omega prime be any positive numbers and let n of eta n eta omega omega prime be the number of solutions of this inequality u omega plus v omega prime less than or equal. Okay. This is the number. So count this now. Okay. Now, as we know that if you take u omega plus v omega prime is equal to eta, this is a straight line, right? And what kind of straight line is that one? So if you put it, this is O, and let's say this is the line u omega plus v omega prime is equal to eta. So this is the u axis, this is the v axis, and therefore this is when v is equal to 0, you have intercept n by omega prime comma 0, and this has intercept 0 eta by omega. Okay, therefore this is, and we want to count the number of points in vector as that is the problem. All right. So by general principle, since the number of lattice points is equal to the area plus error is order of the perimeter, therefore this n eta would be approximately equal to 1 by 2. Area is eta by omega prime. Okay, this into length into height plus order of eta. So this is the first approximation, first result. Equal. Now can we do better than this? All right. And Hardy studied extensively about this problem and observed that the number of points inside this are same as if you take another triangle with sides k eta, k omega prime. All right. because when you multiply everywhere k, the k cancels out. Therefore, the observation is that improving on this error depends only on the nature of this omega and omega prime. Rather, so remark can come, improvement depends on the nature of this number theta, which is omega by omega prime. So what is this number omega by omega prime? All the improvements depends on that. And later Hardy proved, he showed that the number of points inside this rectangle is eta square by 2 times omega omega prime plus eta by 2 omega plus eta by 2 omega prime as given, the main term as given by Ramanujan, with the error that Hardy computed r eta, where you can write r eta as, this is O of eta for all rational theta. That means if this theta is rational number, then this is O of eta. And this is little o of eta. You can show that it is little of eta for all irrational theta. And this is little o of eta by log eta when theta is log 2 by log 3. That is in the Ramanujan's case, this omega by omega prime, right? So log 2 by log 3, if you take in the Ramanujan's case, this is little o. I hope you understand what is O and what is little o. You see, you say that f of x is O of another function g of x, provided fx by gx is bounded some constant as x goes to infinity. All right. And you say that fx is little o of gx if fx by gx, it goes to 0 as x goes to infinity. All right. So this is a simple meaning of all these things. Therefore, see, in the case of irrational theta, from the trivial estimate that we get O of eta, Hardy could improve that it is in fact little of eta here. All right. And in the Ramanujan's case, it is in fact much better, eta by log eta. All right. In fact, later, a little later, Hardy and Littlewood they studied it further and they observed that in fact in the irrational case, if theta is irrational, it has a continued fraction expansion, and let Pm by Qm be the mth convergent of theta in the continued fraction expansion of theta. So if the convergents, the denominators of the convergents, if they grow in the way, in the fashion that the m plus 1th convergent is bounded by mth convergent to some number alpha naught, where 1 is less than alpha naught, okay, with a bounded number alpha naught. Then they showed that this error term is in fact O of not eta but log eta. Okay, much better. This happens if alpha naught is equal to 1. So Qm plus 1 is bounded by Qm. Then they showed that R eta is O of log eta. And in all other cases, they showed that this is O of eta to the power 1 minus 1 by alpha naught plus epsilon. Of course, this O term depends upon epsilon. So this is otherwise. All right. So this is what they have shown. More recently, in a comment in a paper, we have commented that this is with Ramchandra, my thesis advisor, Professor K. Ramchandra, and with my senior colleague A. Shankar Narayanan. And myself, we made an observation that if theta is quadratic, irrational, then you can make R eta as O. Okay, and if theta is any algebraic irrational, if theta is any algebraic irrationality of degree at least 3, the irrationality measure of theta is at least 3, then R of eta is O of eta to the power epsilon. Okay? For every epsilon positive. And in the Ramanujan's case, if theta is log 2 by log 3, then R eta, we showed that O of eta to the power 1 minus 1 by alpha naught plus epsilon. This is same as this one, Hardy and Littlewood, but we were able to compute alpha naught to be 2 to the power 40 times log 3. By the way, these are very small numbers in number theory, okay, particularly in analytic number theory. All right. So this was possible by means of some results of Baker and Westholz. And much more recently, Karthik Babu, the student from IMSc, and Usha K. Sangle was a postdoc here. They showed, they studied this problem extensively. They proved many results, and one of the results implies that this alpha naught can be taken as 2 to the power 18 log 3. 2 to the power 18 log 3. I mean less than or equal to 2. This is a more recent result which is going to appear in Proceedings of Indian Mathematical Society, Proceedings of Mathematical Sciences. All right, the recent version. Okay, so these are the results that we have. Just one or two lines proof of how one estimates this one. So one looks at this triangle. This is O, and this is eta by omega prime 0, and this is 0 eta by omega. Okay, and this is the curve u omega plus v omega prime is equal to, this is the line. Okay. So now the idea is to count the number of lattice points inside this one, right, as eta goes to infinity. So this is u, this is v. So take any u is equal to n. N is an integer. Count the number of lattice points on this and vary this line from here to here. So on each line, count the number of lattice points. Vary the line from u is equal to 1, 2, 3, 4 up to eta by w. All right. That is the basic idea. So observe that the number of lattice points on the line. On this line, how many lattice points are there? So what is the intersection here? Okay. So here the u part is n and the v part is eta minus n omega by omega. These are the coordinates of this. So if you take any line, let's say this is the x-axis of length, let's say 11.3. How many lattice points will be there on this? Okay. So this is 1, 2, 3, 4, 5 up to 11 here. But there is a 0 also. So this is integral part of 11.3 plus 1, right? On this line of length, this one, this many lattice points are there. So here, the length of this is eta minus n omega by omega prime. Therefore, the number of lattice points on that line is 1 plus integral part of eta minus n omega by omega prime. Now, to vary the line from n is equal to 1, 2, 3, 4 up to eta by omega prime. So, therefore, you get the total number of lattice points as n up to eta by omega 1 plus eta minus n omega by omega prime. All right. This is the first step. Now, remove this integral part. So, you see the integral part is the number x is integral part plus fractional part, right? Or the fractional part is x minus the integral part. Okay, this is the normal thing, but many times it is better to write x as x minus half. Substitute this one. All right, this has very nice mathematical properties. In fact, if you sum these things, you can show many nice analytic properties of this expression. I will not go into that. So by this symbol, you can write n of eta. By opening up this integral part, you can show that this is nothing but n less than or equal to eta by omega. This is eta by omega prime plus half minus n times omega by omega prime minus eta by n omega by omega prime. This is the point. Okay. And then, one estimates these things, but these are simple sums. Okay. So this sum estimation of this gives eta square by 2 omega omega prime plus eta by 2 omega plus eta by 2 omega prime. Okay. And with a small bounded number. And estimation of this is the important. Okay. This is the fractional part which is converted into exponential sums and estimated by means of the convergence. This estimation is done. I will not go into details of this, but what Hardy and Littlewood, they show that, in fact, this is by looking at omega by omega prime, they show that this sum reduces to O of eta by Qm plus O of Qm. All right. And once you have this sum to be of this much, then the thing is to choose judiciously Qm. All right. So the various choices of Qm gives you the results that I have stated before. All right. Namely, if Qm plus 1 is of the order Qm plus alpha naught, then you get this one. You can show that this is O of log of eta. In the case alpha naught is equal to 1, and it is in the case eta to the power 1 minus 1 by alpha naught plus epsilon otherwise. Okay. So it follows from these things. I will not go into more details. I would say that those who are interested, these things are available in detail. You look at the beautiful book by Hardy. This is on Ramanujan, 12 lectures on Ramanujan. Okay. 12 lectures by the life and works of suggested by Ramanujan. Okay. And the other one is about Ramchandra's paper and my paper, Shankar Narayan's paper and mine. This appeared in Hardy Ramanujan Journal. You can Google it. The last one by Karthik and Usha. This is yet to appear. I suppose, I don't know whether it has appeared or not. Proceedings of Mathematical Sciences. So I think I will stop it here and invite questions if anyone has any questions. So I have not seen the laptop, the chat box or anything like that. So please let me know if there are any questions.
Yes, sir. A few questions are there.
Yeah.
So from the beginning itself, the first one is, are the lattice points corner points of the squares Qi or rather centers of Qi?
Are the lattice points?
Corner points of the squares Qi or rather centers of Qi?
No, to each point, each lattice point you associate some square, which is convenient to you.
That corner points are actually
so if I have one, so I can either say that this point is associated to this square. Okay, then there is another lattice point, then I will draw another square. I will say that this square is associated to this one. So there will be one-to-one correspondence.
So will boundary points be counted?
Boundary points of?
Inside the circle, when we consider inside circle?
Yeah.
This part.
That's the reason why I'm taking a circle which contains the area of all the squares, the larger circle which contains the area of the squares. Okay, so that the number of lattice points is less than the area of the larger square and is bigger than the area of the smaller square. So that gives a very good approximation of these things.
So will it contain the boundary points too?
Boundary points of
Circle are also counted.
yeah.
Yes.
If there is any point here, so I'm also taking a circle like this, right?
Yes.
This thing square root of 2. So my larger circle already contains this one.
Yes.
Yeah. That's it.
Okay. Another question is also related to that. When we consider the unit circle, the number of lattice points, whether it will be 1 or 5. So it's of course 5, no?
If we consider the unit circle.
Unit circle with center origin.
See, unit circle, we have, the center point and then, the
4 points.
Yeah.
Yeah.
This is 1, 0, 0, 1, and all these things.
The same question, sir, whether the boundary points to be included or not.
Yes.
I think that's all the questions in chat box. So I think participants.
So I will stop sharing.
Queries. Okay. Sir.
Yeah. So
Answer.
So fine. Any more questions? Anyone? You can also write me email if you want to discuss some further things or you want to know more. Anyone? That's it.
So that lattice points visible from the origin, it was an older problem compared to this one?
The visibility problem is different.
Yeah, different. That lines through origin.
Yeah. That's a different ball game. So we can
It's
have
older.
another talk on that.
Okay. It's older than these problems, or?
Yeah, that's a different type of how many points are visible from the origin. That has a different analysis altogether. That's also a classical problem. A lot of development have happened.
And also we have considered a circle, hyperbola, and right triangle circle. Is there any relevance for considering ellipse or directly?
Yes. There are, you take any simple, there are lots of results. I have only touched upon these 3 simple
Yes, already touched.
Yeah, so because if I deal with too many things, then, it may become a little wayward. So, just wanted to show, that even a little bit of improvement requires a new idea. Okay, one may improve in the 4th decimal place for a non-mathematician or for a non-number theorist. I mean, I'm particularly talking about analytic number theory. It may look very insignificant. What is the point in improving in the 4th decimal place? But actually, it is considered a very big achievement, even if you improve in the 4th, 5th decimal place.
Anand sir has joined.
Yes.
Any more queries? I think, sir, no further comments.
Okay.
From participants. I think they all wanted to contact you personally.
Sure.
They also need the PDF, asking for PDF of all these talks.
I have a I have given this lecture somewhere else. I can send the PDF file of that.
Okay. If it is available, we will send it.
I will send it to you. Then you put it. Okay.
The way you wrote the notes, can't you save the PDF right now?
I can share the PDF right away.
I have never done this, but I think it's possible, right?
Okay.
Huh? Sorry.
The notes that you were lecturing on the iPad or something, no? So there itself you can save the PDF, maybe, no?
I can send it right away. Yeah, I can send that. But
save.
Yeah, I know.
Same
But
thing, I think.
my original PDF contains much more.
Okay.
Because that contains exact statement. I did not mention the results of Karthik and Usha here because they are 1 page long. I mean, the statement itself.
The details they want, I think, because the slides we can show here. The meet recordings we are giving to them.
Yeah. So the
slides,
same lecture I gave in ISI, where more focused audience were there.
Okay.
So I could talk by assuming many things here. I didn't speak all these things.
Yeah.
But here, since it's a general, students are there, I wanted to go a little slow.
Thank you. So, okay. Then, shall I invite Miss Sona, our MPhil student,
Sure.
for proposing vote of thanks? Okay, Sona.
Sure.
Good afternoon, all. I deem it a great pleasure to propose vote of thanks on behalf of participants present over here on the third day of national webinar on India, Mathematics and Ramanujan. First, I would like to thank Professor Srinivas for the talk on Ramanujan lattice point problem and the valuable information about Ramanujan lattice point problem and Gauss and Dirichlet lattice point problem. Thank you so much, sir. Also, I express my gratitude to all the teachers and staff Department of Mathematics, Calicut University, for organizing such a wonderful opportunity for us. Also, I thank all present here paying attention and learning. Thank you.
Thank you, Sona. Sir, so we will contact you, sir. We should plan some programs here for students as well as teachers. So sure, we will contact you all for help, support. So your mic is mute.
Yeah, you can think of having the teachers program that I was talking about.
Oh, yes.
Yeah, you can think about that. You can organize it this year.
Okay. Last year it was conducted, sir?
Yeah. Last year many programs got cancelled.
Yes.
Right. But this year online programs are on. So you can have a look at this website called National Center for Mathematics, where Anand is also a member of that committee. So look at that National Center for Mathematics that has plenty of programs.
Okay.
And think of having some program that suits you and
okay, sir. So sure we will consider.
Hello, sir. Once again, tell sir that committee name, sir.
Sorry.
NCM.
Good afternoon, sir. Can you tell me, sir, that conducting program you just told? What is it?
National Center for Mathematics.
Okay.
NCM. So you should type ATM schools. If you're googling it, Google it. ATM schools. If you type, it will take you to that NCM school.
Okay, sir.
It's in
Thank you
IIT
so much.
Bombay.
Okay, thank you, sir.
Nice to see you, sir, here.
Yeah. I'm very happy to see you and your kid also.
He just woke up.
Sir Prasad, sir, Anil sir, you are here?
Yes, I am here, but my video is not working.
So sir. Prasad and Mubina joined recently, sir. And now we are 5 faculty members here.
Mubina, you have moved to from you were Cochin University, na? You were in
No,
last time when I saw you, you were in Cochin University or?
no. I was in government college, Kasaragod.
Okay.
Now I moved to here. In
I
this
see,
month
I
only.
see.
This month only I
Oh,
joined.
okay. Very good.
Lucky to see you from university.
Yeah, she did her PG from here.
I did my PG there.
Sir, one more I request you, sir. Sir, can you provide your research paper?
Yeah, I can. You look at the recent one, that will give you more information.
Okay, sir. Okay.
You write a mail to me, I can send you.
Sir, can you provide your mail
Yeah, Srinivas,
in chat box?
Srini,
SR
at imsc.res.in.
Okay, sir. Thank you so much.
So, shall we call it a day then?
Okay, sir. We can conclude this session. Yes, sir. No further queries. Okay, sir.
No further queries then.
Yes.
Okay, then you can close it.
So, thank you,
Okay,
sir.
thank
Thank you
you
so
very
much.
Thank you,
We
sir.
will,
Bye.
we will meet again, sir.
Yeah,
Okay.
sure.
Bye, everybody.
Bye.
Bye, sir. Anand, sir.
Okay.
Anand,
Thank
sir.
you. Thank you, sir.
Thank you very much. Bye.